We're going to make a start now, and I'm very pleased to welcome Neil Brown. Neil works at SUSE. He's been a kernel hacker for 10 years plus, and his title of his talk is Wiggle While You Work. So just please.
Thank you, and thank you for coming. Today I want to talk about a problem and a solution. I guess an itch that I wanted to scratch. A story that starts more than 10 years ago. It's an issue I was thinking about and grumbling about to myself and not doing much about around about 2000, sometime 2002. And I started thinking about a solution, and then at some point I started writing a solution. I can't remember whether I started writing the solution before or after Andrew Morton made this quote that I've got up on the board, but it exactly fitted with the ideas I'd been having, and hence I chose a word out of his quote as the name of my project. The problem, he says, that he finds is that I often want to take a file plus a patch, where the patch doesn't apply perfectly, and merge that to create a new file, but all the merge tools take a file plus a file to make a new file. I haven't seen a graphical tool which helps you wiggle a patch into a file. So I wrote a program that would wiggle a patch into a file. And for a long time it wasn't at all a graphical program, because I found I could actually solve 90% of the problem with just, command line and text, which is where I'm most comfortable. But that eventually proved not to be satisfactory sufficiently that I progressed more, and so I want to talk a bit about that too. What is the problem exactly? Well, I've been a kernel developer for a long time, and one often needs to apply patches that were developed against one kernel against another kernel. So particularly, for instance, working for SUSE at the moment, we have an enterprise kernel that's 1, 2, 3, 4, growing every few months, versions behind mainline. So I do develop on mainline, and that's policy. We should always do develop on mainline. That's a good thing. Then if I want to apply these fixes to the enterprise kernel that we actually support and get money for, got to backport them, and sometimes that's really easy, and sometimes that causes problems. And when it causes problems, you really want to focus on the semantic issues, whether it's actually going to work. You don't want to be caught up with silly syntax. And patches not applying is just boring. Equally, forward porting, occasionally one might fix a bug in the enterprise kernel and then need to port it forward to a newer kernel if it's still relevant. One might get a patch off a mailing list and you don't really know what kernel it's for, and it might not apply to the one you've got. And you could just send a mail back saying, can you just give it against the current kernel? But sometimes that's putting too much of a barrier to entry. And if I can just wiggle it into place myself, then it's a lot easier to do that. And of course, it's probably not just the kernel this applies to. I use it mostly for Linux kernel. That's mostly where I spend my time. But I have actually used it for other packages as well. And yeah, it works with any source code, of course. And when you have a patch that doesn't apply, patch itself isn't much help. It tells you, failed. I failed to apply that. Here it is in a reject file. Or I applied it with, there was some fuzz. Does everyone know exactly what fuzz is? So fuzz, we'll see fuzz a bit later, but fuzz means the patch contains so much context, and I couldn't find a match with all that context, but if I throw away a little bit of context, then I can find a match. So fuzz of 2 means I threw away 2 lines of context. And an offset of 514 lines. Was there really 514 lines that maybe got it in the wrong place? And you can't really see what's happening. Now, this is what patch produces when it does a fuzz, it just puts it in. When it can't find a reject, it shows you that. There's a little patch with 1 line that's been added into the middle of it. And you think, well, that's easy enough. I can probably take that and edit the file and put it in. It's not really that hard. But this is a really simple example because I won't fit on the screen in a big enough font. Most examples that are really interesting are maybe 20 or 30 lines. And you can't just eyeball that and see what the issue is. And I remember using Emacs macros to try and help me, and it was never very satisfactory. A few years back, 2009 I think it was, patch grew this -- merge flag. So instead of putting the patch in a .reject.reg file, the missing bit in a .reg file, it puts the missing bit actually in the file itself where it thinks it was meant to go. And the guy who did that, Andreas Gruenbacher, actually, it was motivated to some extent by the way Wiggles work, because Wiggle does something like that. And so there we see inside the file, it's done similar to what diff3 does, not exactly, some less than signs, some equal than signs, this is the text that was meant to go here. I actually find that particular example there is fairly problematic because it looks like, if you look at that, you can see a spin lock init and a spin lock init, and they're probably the same spin lock. And then there's a for loop that's structured differently just after it. And then you can see the added struct request QQ, which was added previously. You can see that thing struct request QQ was added there. Well, you can see it's there as well, so you know you've got to add that. But it looks like you've got to add the error equals dash e inval as well, which you don't. So that output of patch is actually fairly poor, unfortunately. What it should look like is more like what diff3 does. And Git, I think Git's, Git is different to patch because Git has the entire file, not just a patch, and that makes a significant difference we'll get to in a minute. But when Git finds a conflict, it tries to merge it. The default merging, I think, is kind of unreadable. It doesn't really give you enough information. If you set the merge.conflict for Git to diff3, it actually shows you a result like this. So you can see the less than, the vertical bars, equal signs, and the greater thans. The first section is essentially what I found in the file. The next section is what I expected to find in the file about here. And the third section is what I was going to change that to. So once you get into the habit of reading that, it's quite easy to see that what that's saying is, I wanted to add a struct request somewhere near this RDEV for each, and you can see exactly where it's meant to go from that. So again, in this case, doing that by getting that output and fixing by hand is fairly easy. And in fact, that's exactly the sort of output that Wiggle, the command line version of Wiggle, produces if it can't do it itself. Right? It'll produce output like that, and you get to look at it, and 9 times out of 10 you can fix it by hand fairly easily. But you really want Wiggle to fix it for you if it can, because that, if you think about it, it's a fairly easy fix. And this is what Wiggle does. See, there's nothing, it's exactly done the right thing. Wiggle running on that exact diff, applying to that exact file, gives there. It's just put struct request queue thingy in exactly the right place. And this is where Wiggle stood for quite a while. It would do this, and I had a little script that would, whenever I got a reject file, I would give the reject file to Wiggle, and it would throw the result up in an editor, and I would fix it. And it was mostly good, but the problem is, it can be a little unnerving. It just works, and you know there was a conflict of some sort. You know it shouldn't have worked perfectly, and it did work perfectly. It probably got it right, but I want to be able to see what it did. Because sometimes it makes a terrible mess, which is all right because it keeps the original file, and you can put the original file back. It's not destructive, and you've probably got the original in Git or whatever anyway. Sometimes it does make a mess. So what I've added more recently to GIF is a cursors mode, an ncursors mode. So you run it in your Xterm, and it pops up kind of like the eye or whatever, and it shows you the text with little highlights everywhere. So if you can see here, you can see that section. In fact, you can see everything that was patched by that patch before. You can see the green, the plus green, where it's added the request queue. And you can see lower down, there's 3 other green lines that have been inserted. If you see those green lines, there's one black line above and one black line below. Actually, there's 3 black lines below, because one of them's all empty lines, so you can't see it, it's black, I promise you it is. And there's 2 black, I'm not sure if there's 1 or 2 black lines above. But anyway, that's enough context for patch to have said, yes, I got that with the fuzz of 2. Wiggle just doesn't worry too much about fuzz, it just, yeah, it must be right, stick it in there. The other bits and pieces, you can see, so we'd already figured out that the file that was being patched had this list for each entry sort of for loop, whereas the... Did I get that right? Yeah, the file that was being patched had a list for each entry, whereas the patch thought that was a different form of list for each. It was a RDEV for each or something, a more specific macro. And so you can see the blue text is the text that was in the file, but wasn't in the patch at all. So this is something that was in the file, and you expect the stuff at the bottom and the stuff at the top to be blue because the patch doesn't have that much context. But stuff that's actually in the mix, in where the change is happening, there's bits of blue, bits of black. That kind of shows you where Wiggle kind of found, it's close enough, this definitely looks like where it's meant to go, stick it in here. And the closed parenthesis and the open curly bracket and the new line all matched, and that was enough for Wiggle to just say, yes, this is where it goes, and put it in there. And you can read a lot of that out of the colours once you get used to it, but sometimes you really want, well, what exactly was the diff again? So if you move the cursor actually into a conflict, it splits the window and you can see down the bottom exactly what the diff was, and then at the top you can see how it tried to apply it. So in the diff now you can see some bits that are meant to be cyan. Not sure how well they turn out on the screen in this sort of light, but so the bits in cyan are bits of text that were in the diff and didn't really match anything at all in the original file, much like the blue is bits in the file that didn't match anything in the diff. And so you can see that to some extent a bit of blue in the file has replaced a bit of cyan, and they kind of line up, they semantically line up when you look at it. So you look at that and say, yeah, all that adds up, that's good, I'm happy with that patch. And so it just gives you a bit more confidence. I mean, Wiggle did the right thing, and Wiggle usually does the right thing. And when Wiggle can't do the right thing, it's often there's nothing right that can be done, like that the bit of code that's being changed just doesn't exist anymore sometimes, or it just has to be completely rewritten anyway. But so it gives you a bit of confidence, which is good. I like confidence. So how does it work? How does it work? This is the fun, interesting bit to me. Now we've seen that, why does it work? Well, it does a couple of things. First, it creates two diffs. A diff, we'll have a picture of this in a minute, so you don't hold too much of it in your brain at once. So it creates a diff between the file that you're changing and the first half of a patch. So it takes a patch and it breaks it into two bits, the before bit and the after bit. So all the context and all the minus lines are in the first bit, and all the context and all the plus lines in the second bit. Then it does a diff between the original and the before bit, and rediffs the before bit and the after bit. And then it kind of lines them all up and produces 6 different sorts of mappings, as we'll see in this pretty picture that I've got. So here we have the original file. The file I'm being patched contains this one line: the quick brown fox jumps over the lazy dog. And we've got a diff, and the diff has got 2 hunks. You can see the ... separates one hunk from the other. The first hunk says a quick brown fox should be replaced by a slow brown fox. The second hunk says jumps over the idle dog should be replaced by second hunk says jumps under the idle dog should be replaced by jumps over the sleeping dog. Right? And now you can see, so we did a diff between the top 2 bits, and those double-headed arrows show you what similarities it found. It found that quick and quick are the same, brown and brown are the same, jumps and so forth, but there are some bits that didn't match. And similarly, it did a diff between the before bits and the after bits and lined up all the bits. And then it tried to line them together. And obviously so black bits are bits that are unchanged. It found something similar between the original and the before, and the same similar thing between the before and the after. That all lines up, so that's an unchanged bit. It's a significant bit of context. It's hopefully reliable. It also found some unmatched stuff. So the blue stuff here again is unmatched. It's bits. So anything that was in the original, but it didn't find a match for in the before, but also at that same sort of point, there's no difference between the before and after, then that is unmatched. Similarly, if there is the matching bit that may not exist, it might be empty, but the matching bit in the before and after is then an extraneous. So you often see unmatched mapping with extraneous. Obviously there are changed bits, they're exactly what you'd expect. You know, the original matches before and then it's different in the change. Those are the good bits, those are the bits you actually want to apply. And then there are conflicts. And really there's only one, there's a subclass of conflicts that I call already applied. A conflict is where the original has X and the before has Y and the after has Z. It doesn't seem to line up at all. As in this case where the original said it was a lazy dog, but the patch said it wanted to change an idle dog to a sleeping dog. There's no way you can automatically resolve that, right? No matter, even if you could semantically analyse the sentence, you'd have to figure out what the author meant to be able to. So that's just something Wiggle has to say, look, this is a conflict, you resolve it. whereas it tries to it resolves everything it can, but there's something it can't. The magenta one there, the already replied, was where it was jumps. It found jumps over and wanted to change jumps under to jumps over. Well, it's probably like someone else has already made that change. We can just ignore that. You can tell wiggle to ignore already applies, always treat them as conflicts, but almost always it's doing the right thing. Yes, Rusty?
So is this done, is this just your example, or is this really done on some sort of parsing tokenization basis or character basis?
It's done on mostly on a word. So it breaks it up into words, where a word is either a string of alphanumerics, or it's a string of spaces and tabs, or it's a single character. Right, so all punctuation is just a single character, which comes up as a bit of an issue in a few slides later, but yeah, I was meant to mention that. So as you can see, it parses the two different common sublists and creates a list of merge elements, which are one of these 6 types. And kind of figuring that out came a bit late in the piece. I had all this code that kind of tried to work it out and print it out as it happened, and it was way too confusing. And once I figured I could kind of see it like that, it made the code a lot simpler. So anyway, it breaks up and finds those 6 different types of elements in the whole complete thing. And then once you find a conflict, when you display it to a user, when I show it to you, you probably don't want to see the conflict in the middle of a line. You definitely don't want to see a conflict that runs from the end of this line to the beginning of that line. It's too hard to read. So it'll expand the conflicted area backwards and forwards, roughly until it hits a couple of new lines, until it finds something that looks stable enough. When I was writing the slides, I thought, yeah, that's really simple. And I looked at the code after, and I thought, it's actually a bit more subtle than I thought. But basically, it moves it backward, expands it until it can print it out meaningfully as a whole number of lines that it thought it was going to find, a whole number of lines it did find, a whole number that it thought it would find, a whole number of lines that it wanted to replace it with. And then once you've got all these ideas, you just dump the output. You either print it out in text, save it, it'll replace the original file, or it'll write it to standard output, whatever command line arguments you give it, or it can display it in an in-cursor window for you. So yeah, I just wanted to highlight here that we'll create this data structure I call a merger or a merge or something, that each merge element refers to a sequence of characters in each of the 3 streams, the original, the before, and the next. Some of those sequences might be empty, like if a deletion, if you just delete a line, then the original bit and the before bit will be non-empty and the same, and the after bit will always be empty. So in some cases, for some types, one part is always empty. For other types, one part is sometimes empty. And yeah, so it's just a nice, simple data structure. And that was necessary in order to be able to render it and move up and down around it, sort of draw it on the screen in colour and move up and down around it. Expanding conflicts is fairly simple. Walking backwards from the conflict merge point until you have enough context, which is approximately 3 whole lines, which is the same sort of context that diff uses. I found early on that often when it showed me a conflict, there would be so little context to the conflict. Particularly, it was throwing away extraneous lines because they looked the same and they didn't seem important. But I realised I needed that, so it was only earlier last year I sort of extended the context. And I think I've actually extended the context a bit too much for some cases. But you know, there are so many different examples, it's hard to pinpoint exactly what you want. So I've got a bit of a test suite to test out any changes to see if they make anything look really horrible. And so I mark all of those, mark a whole range of merge points as in conflict, and then I can handle them differently and sort of go backwards and forwards to do that. And then just print it out. So loop through the list. For each different type of merger point, it's obvious really what to print out. And when you get to a range of points that are in conflict, you have to print the whole set 3 times. First you print the bits that were before, and then the original, then before, then after. But there are difficult bits, so those are the easy bits. It's kind of difficult, I discovered, to create a diff between the original file and the before part of a patch. Because the original file is big-ish, and the before part of a patch is, 5 or 6 little hunks that line up, hopefully in the same order, somewhere in this file. And importantly, where a hunk matches the file is probably all still fairly close together. There's probably not really big gaps in it. So another way of saying that is when you match a relatively small before bit of the patch with a relatively large file, you're obviously going to have some large bits that don't line up. All those large bits that don't line up really have to line up with the break between the patch headers, between the hunk headers, right? So that basically the chunks need to match close together bits. And so to understand that, and because I think diff is a really cool algorithm, and because I've got some pretty pictures, I want to just go through, hopefully fairly quickly, how we actually do a diff. And then I can explain how we modify the way we do a diff to actually line up the chunk hunks, what are they called? Hunks, I think diff calls them, with the original. So as we'll see in a minute, a diff sort of actually explores a quadratic array, but storing this quadratic in the size of the files, which might not be too big for today's computers, but certainly back when the diff algorithm was invented, it certainly was, and it's a waste of space. You don't actually store the entire array, but you've got to conceptually explore that. And so we'll see there are diagonals, and you only keep 1 point on each diagonal at a time. And so when we get to the end, we don't actually remember the exact path we went through, the optimal path. We'll just remember the halfway point of the optimal path. So as we go through, we measure the halfway point of each path, which is only a log n, order n amount of data you need to store. And when you've found the halfway point, you recurse on before the halfway point and after that halfway point to build a full path. So here we have a sample diff, complete with the matrix, the matrix that we have to explore. So across the top, there is a sentence: the slow brown fox raced a quick brown fox. You can see I like foxes. Down the side we have the other thing we're matching it with, or comparing it with, the quick brown fox won. And so there are one more dots you can see than words. A word corresponds to a line in the matrix, an edge in the matrix going from across or going down. And going across is equivalent to deleting a word in the original, and going down is equivalent to adding a word in the result. So if you went all the way across, the path all the way across and all the way down is basically saying all of that, remove all of those lines and add all of these lines, and the cost of that is, I can't remember, it's about 12, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The cost of that path would be 14. Right, all the way. And obviously if you came down, added all the new words and deleted all the old words, the cost of that would be 14 as well. But as you can see, there are some red diagonals that line up exactly where a word in the two lines match up, and the cost of those is 0, as you can imagine. So you want to find a path through the matrix from the top left to the bottom right that minimum cost goes through as many of those red bits as possible. But we don't want to actually store the whole thing in memory, so we just store the stars, the yellow stars and the blue stars. I should just, a helpful aspect is the fact that each different point in the matrix, some of them always have an even cost, no matter what that is. Some of them always have an odd cost, no matter what that is. In this case, the yellow ones are all odd, blue ones are all even. So points with a cost of 0, obviously you would think at the very beginning the top left point is a cost of 0, because there's a red line there, because the matches the, you can go straight down to that second point where the yellow star is, and that is the only point really of interest where cost is 0. And to find points where the cost is 1, we start with the 0 cost points and just go down and across. And we get the 2 blue stars that are down and across. And those are the only 2 possible points with the cost of 1. And then we step forward. And you see now we've moved the yellow stars just after the blue stars, just to the left. So from a blue star you go just to the left and just down. And those are where all the new yellow stars go. One of those points is on red slopey bits, so it slid all the way down, because that's all of cost of 0, because brown fox matches brown fox. And you see it's just across the magenta line, which is the halfway mark, halfway from the beginning to the end. And so that the memory location, the base entry in an array that corresponds to that particular yellow star will now remember that there is where it crossed the midline. So if that star ends up winning, getting to the endpoint first, then that's where we'll come back to recurse, do a binary search. Then from those yellows, we step forward to find new blues. This blue down the bottom looks like it's winning, doesn't it? And then from those blues, we step down to find the next yellows. And then from those yellows, we go to the next blue. Oh, look, the blue one hit the quick brown fox, matches quick brown fox, and slipped all the way down. It looks like it's going to win, and in fact, it does. We get a yellow one down here at the bottom. So because we've got really complex memory systems, we can remember exactly what that path was, and because this is a really simple example, but in a more general example, the information stored in that yellow star is simply what point on the magenta line it crossed. And seeing it was first, it wins, then we go back and recurse. That's how diff works. And the fact that it runs down those red lines whenever it finds a common bit, because those red lines really have zero effect on the score for each point, you can just zip down them quickly. And that's an important... You can see all these other stars are still miles from the end point. We don't have to follow them all through to the end and figure out which the best score was. We know nothing else is ever going to get better than this score, because they've all actually got the same score at the moment. And so being able to run down those red things is an important thing in making it go at a reasonable speed. And now I've just got a slide with some of those points I said to make sure I actually said them all. Horizontal lines, deletion, cost 1. Vertical lines are insertion, cost 1. Red diagonals are match, cost 0. Yellow dots are even, blue dots are odd, and so forth. Each star costs. So I think I said all those things, and hopefully people will read the slides later, get some idea. Now, you might have noticed that example was carefully constructed because you could imagine that the left-hand side was just a lot smaller than the sentence across the top. The quick brown fox one is a lot shorter. And the place it chose to match, it matched the first word and the last few words. It couldn't find one anywhere, but otherwise than that, I'll just go back so you can see what I'm talking about. It ended up matching the first "the" and then the last 3 quick brown fox, and couldn't find any match for one. Which, if these are complete files, that's obviously the best match. But if the quick brown fox 1 was actually part of a patch and you were trying to find the best place to align it in that file, well, the best place to align it is probably either aligning it at the front with a quick brown fox or aligning it at the end with the slow brown fox. But aligning it with the whole stuff is just not where you'd expect a patch to be. And in my early iteration of this program, of my tool, I found that Wheel did exactly that. If a patch hunk didn't match perfectly, it would match it with all sorts of wrong stuff. And so we need to modify, as I said, the diff algorithm. So those stars, which essentially, as I said, correspond to an entry in an array, keeps track of which patch hunk it's in. And as it moves along, if it changes from one patch hunk to another patch hunk, it's just got to reset its scoring mechanism. And it keeps score kind of how close together the current match is. And inserts and deletes have sort of a higher cost. A cert and a delete right next to each other is considered to be a replacement, so it's got a lower cost. And if you have a few matches and then a long period with no matches at all, the total cost ends up going, the way it works, goes negative, and so it just forgets about the early part. So in that case, hopefully it would have had an option to forget about deleting "the" and then just match stuff at the end. And then each star records what hunk it's in, and when a star changes from one hunk to the next, it records in a separate data structure for that hunk what the score was. So by the end of the time, you know what the best score for each hunk was. And sometimes that can actually result in the best scores being achieved by reordering the hunks. I'm not sure. Currently, I just insist on forcing them to be ordered. So I pick the best one and move them around until they are in the right order. Though, of course, sometimes you do reorder code in a file, and sometimes you actually want them to change order. So I don't know that I've really had that happen in practice enough to want to worry about it. It would need to happen a few times before I sort of had enough data to think about it properly, but there might be some room to make that go better. And this ran significantly more slowly when I first implemented it, obviously on a computer that was nearly 10 years older than my current one, but it did. So, and that's because it couldn't slide down the red slopes, because of the way it kept the scores, it couldn't slide. It had to go lockstep. The yellows would just overtake the blues would overtake the yellows, would go the whole way through. And so I had this brainwave. I just throw away all the uninteresting words, because when you break the file up into where every punctuation is a single word, that ends to be a very large number of words. And because it was slow, and the punctuation probably isn't that important for localising a hunk, so I threw them away, just kept the alphanumerics, and then it went at a much more reasonable speed. And once I got roughly where the hunk should apply, I could then bring all the other words back in and make it work. So where is it? Well, it often works, but occasionally makes a bit of a mess. And I said this wiggle-r foo.c, foo.c.reg, I've got a script that does that. It does that, then throws me into an editor for foo.c and fixes everything up for it. That's how I use it for a long time. I don't think Git's merge resolution is as good as I'd like it to be, and Git's very configurable, so you can tell Git roughly like that to use wiggle to merge things. You can give it a patch and browse a patch. So I've given it this patch, and it's shown you all the files with colour codings. And the numbers at the front, the first one is how many patch hunks. You can never decide if it's hunks or chunks it found in the file. The second one is how many of those it had to wiggle in place, they weren't perfect. The third one is how many of those caused a conflict. The conflicts are in red, so you can find them and go and look at them. There's inline help. If you want to play with it, just type H and it gives you little bits of help all the time. Do I have time for a little demo? Yes, I do. So I just wanted to show you it running. Here's one I prepared earlier, which I can't see on my screen. There we go. So I'm in one and I say wiggle-bp patch. And so this is, I thought it would all fit. That's odd. Hopefully it'll work like that. So this is, I don't know if you've heard of DM Thin, the thin provisioning layer for DM that was added in the last year or so, and we wanted that now SLES 11 SP something or other product, and so I was backporting all the patches, and most of it went really smoothly, but sometimes I hit issues, and so I thought I'd collect the issues and show them to you today. So obviously a lot of those files worked, but this one didn't. So I just go down there and press space, and here it is. And I can go through it just like in kind of a bit of Emacs and a bit of VI. Commands mostly work if you're used to them. So I can use J at this point as well, and it keeps going down. Shift-C, Shift-N will go to the next patch of any sort. Oh, that was interesting. So if you look closely, you can just see that it wanted to delete this message str thing, and it was okay, except the context wasn't quite right, because it wanted to find an include Linux / something, and it found an include a sem / something. So you glance at that and think, that's not interesting. Go to the conflicts, Shift-C, and this I thought was actually a really interesting conflict. So what the patch wants to do is it wants to change this call Shift-AS, which is passed as an argument to some function, to DM Shift-Arg. So I've just changed the name of the function, the shift function. No big deal. But in my code that I've got, instead of doing that function called in the arguments, I do the functional previously, assign it to a variable, and then pass the variable. Obviously, minor difference. And you can edit that by hand. But I was thinking, wouldn't it be nice, because the bit of code it wants to change, the Shift-AS, is exactly there, the line above. Wouldn't it be nice if I could somehow tell it to, instead of applying the patch there, where you can see it's really, that's where it matches best. There's lots of black stuff, which means it found a really good match. Tell it, well, all that stuff isn't really relevant. Just find where that shift matches. That's the important thing. I want to be able to interactively tell it that, and then it would move back up and fix it. I haven't quite figured out how to do that yet. I need to sort of create a list of of examples of these sorts of things. And so I can kind of generalise properly and come up with something that will actually work. So that was the first example. I'll get back out of there and try again. So this is, again, mostly works. Most patches do apply. I mean, this is only, what, about 3, maybe 4 kernel versions. So, not a big deal. What have we got here? Oh, this was interesting because a sort of conflict that it isn't necessarily obviously a conflict is when a patch wants to insert something at a particular place and it finds that something else has been inserted there. You could sort of resolve that, but there's an issue, which order? So it's effectively got two inserts that have happened, probably in a list. What order do you insert them in? And that's often, sometimes irrelevant and sometimes very important. For instance, in this case, where it, so what it's inserted it in is right next to a series of bit fields in a structure. So and this thing itself is not a bit field, so you want to make sure it inserts it outside the list of bit fields or it'll mess things up completely. This has actually provided me a little bit more context in the diff than I would really like. So I think it's again a case of, I'm not sure it's the best way to display that diff, but if I'd want to be careful fixing it because that might break other things. Is there any more? That's all that's in that one. And this one more conflict to look at. C for conflict. Okay. Now, if you look at that for a minute and you think, huh, what's going on there? So you press D and just see the whole diff. And look at that carefully. You see after a while that the original code has got 2 identical bits of code. Some sort of patch problem earlier caused a bit of code duplication. And we're getting rid of one of them. We're getting rid of the top one and changing the bottom one to assign some values instead of to the split IO field, it's assigning them to max IO length. So you sort of look at the diff to have a figure out that's roughly what's happening. And then you look at the original, press O to look at the original, and that doesn't relate at all to the code that's happening there. The sort of the if conditions, the assignments, it's nothing there. So looking at the colours, what are the colours? The black bits and the red bits here. So red bits are deletions, so they're in the original. They were used for lining up. The black bits and the red bits are the bits that it used to line up the chunk, the patch, with the original. And you can see they're kind of insignificant parts of this patch. I mean, the reality is that the code it's patching doesn't exist anywhere in the file. And this is exactly, when you hit a conflict like that, it tends to look really ugly because it shows you what it tried to do, and what it tried to do is a mess. And I wonder if I should have some sort of, presumably the score for the match here was pretty low, and maybe I should have some threshold under which you just say there's nothing worth showing here. But often, one of the usability issues I have at the moment is when there is a serious conflict, I look at it and it really takes me a while to figure out what that means. Where was I? I was there. So that's just the good one. In case I didn't have time, you can see the path and the stuff there. And still to do, displaying conflicts in the browser can be hard to read. I've added some very limited editing. You can tell it to ignore a bit of a conflict, but it doesn't really work very well. So I need to, that's the kind of thing I want to at least make vaguely usable before I call it version 1.0. It's currently version 0.9, so it must be time for 1.0. But the trouble is when I see an issue, I'm in the middle of sort of backporting a bunch of patches. I don't really want to stop, break my train of thought, sit down and think about it. So what I often do is copy the files somewhere and even never get back to them, or when I get back to them I've lost my train and it's kind of hard. Yeah. So any questions? Those are wiggling question marks, which I thought would probably be pretty tedious after a while, so any questions?
Actually, I have a really easy question. Could you go back to the slide where you had the git config?
The very first slide?
No,
yeah.
it was like one before the demo or something. You had a sample git config to use Wiggle.
Oh, right, that one, yeah.
Thank you.
Anyone else got a question while I'm hunting? was near the beginning, wasn't it? Possibly. I mean, you might have noticed I exposed in the top right what sort of conflict I'm over. Yeah, exposing the score might be very interesting in terms of working out what to do next.
Would it make much of a difference what the how the diffs generate in the first place? Like, I've come across this other one called patience diff, which is supposed to be sometimes better at generating a diff that won't create a strange kind of conflict. Oh, sorry, like won't apply as not cleanly because things have moved. Like you said, like you had that example where you could have rearranged two functions so you reorder the hunks.
Yeah.
Which is actually quite common when you're cleaning up files. Well, I do it when I clean up files.
I try not to do it. So I'm not quite sure how. I don't know if patience diff. I don't know how it would produce a different diff. All I can imagine doing is providing more or less context, and almost always more context is better, because you can always ignore context that doesn't match, but you can't really synthesize context that does. And that's, I mean, part of that the matching thing is that it's hard to. I'm trying to figure out what the context was. Yeah.
Back to the first question, can we see that information on the screen, how you integrate with Git? I think it said .git attribute.
Oh, sorry. I found the page and I didn't press that button. That's what you wanted. Sorry. Questions? No?
Is this in a lib or could it be put into a lib so you might be able to integrate it into some kind of IDE with a plugin, or is it really tightly designed to work around your current user interface?
I think the code is fairly well modularized. I mean, it has its own data structures. It would want to, you'd want to give it a contiguous chunk of memory, basically, that contains the text, and do that, and it could produce for you the merge result. So you probably could, as long as you're happy with the interfaces it currently uses. Like the interfaces, the data structure interfaces aren't necessarily designed for working in library, but it's modularized enough that you could probably work around that if you wanted to.
Has it been packaged for distros yet?
It's in Debian, it's in SUSE. I don't know about other distros, but it has, yeah.
So I find a lot of issues when you've simply got, you're basically replacing one thing, which was one of your first conflict example. And I really sort of want a meta tool that goes through and goes, actually I've noticed that you've replaced, everywhere you've replaced this that I can find in the original. Especially that then checks in the result and goes, that's funny because now there are two more that hasn't been replaced.
I've seen examples of exactly that sort of thing happening, yeah. So, I mean, that kind of, it's not really a semantic thing.
No,
well,
it's orthogonal a bit to what you're doing here, but
yeah,
it might be a good partner.
But it would be interesting, yeah. I mean, there's a question of how much do you want it to understand the language, understand the structure of the file, and currently it assumes that kind of alphanumerics and spaces are significant. That's all it assumes. I think it might be interesting to add more stuff like that. It's a good point.
Any more questions? No? Okay, I think we'll just wrap it up here. On behalf of Linux Australia organisers, I'd like to present.
Thank you very much.